Talk for the morning session will be given by Lisa and Hendricks. Lisa graduated recently with a PhD from UC Berkeley and is soon to be a research scientist at DeepMind. She's worked extensively in the field of vision and language, specifically at making models more grounded, explainable, and understandable. Um, Without further ado, let's hear out what Lisa has to say about vision, language, and beyond.
Whoops. Apologies, my computer's old, so it's a little slow. Okay, so I'm Lisa, and today I'm going to be talking about joint work done with Kaylee Burns, Trevor Darrell, and Anya Rohrbach at UC Berkeley, as well as Kate Sanko at Boston University. And I'm going to be talking about bias and how we can diagnose and overcome bias in captioning models. All right, so I'm going to be talking about bias in image captioning, and the first thing I want to think about is if we have a bias training data set that we're using when we're training our image captioning models, what kinds of problems can we see? So one issue that we see is that if our data set is biased, our models might make the incorrect predictions. So here I have an image of a woman in front of a computer, and our captioning model, so the sentence below the image, says a man sitting at a desk with a laptop computer. So here this is an image of a woman, but our model has incorrectly predicted the gender man. All right. So not only have we incorrectly predicted the gender, if we look at what parts of the image are important for making that gender prediction, we see that our model is looking at the wrong evidence. So here I've taken the method GradCam and I've overlaid that over my image to show which part of the image is most important for the outputting the word man. And I see that the model is actually looking at the computer when outputting that word, it's not looking at the man. So not only has our bias caused our model to make the wrong prediction, but it's caused our model to look at the incorrect evidence when making predictions. All right, so what's happening here? So our data set is biased. There's more examples of men in computers in our data set than women in computers, but it's not so much that our model learns this bias, it's that our model, all right. It's that our model amplifies this bias. Okay, so what I'm showing here is I have two pie charts, and on the left I have the distribution of the kinds of gendered words people use to describe images of people and dogs. And you'll see that less than 50% of the time, a little less than 50% of the time, in our ground truth captions, people will use a male gendered term. However, when we generate captions, we see that this bias is amplified, and 57% of our generated sentences use a male gendered term. So in the first part of this talk, I'm going to present a model which will mitigate this gender bias. This was work that was presented at ECCV 2018, and it's called Women Also Snowboard, Overcoming Bias in Image Captioning Models. Okay, so I think that gender bias is really interesting and very important, but if you look at our training data sets, there's lots of other kinds of biases that our models are capable of learning. So for example, usually when people are holding laptops, they have a desk, and our model might learn that desks and laptops are correlated, and this might cause our model to make an error when generating a caption. So here I have an incorrect caption, a group of people sitting around a table with laptops, and here there's people and there's laptops, but there's no table. And we call this kind of error a hallucination error, and we find that a lot of models, image captioning models, are actually prone to making this kind of error, and it's kind of annoying because there's no table in the image. So in the next part of the talk, I'm going to move on and talk about hallucinated objects in image captioning and how we can understand hallucination, and I'll present a metric that allows us to analyze this error specifically. All right, so overcoming bias in image captioning models, in particular gender bias. So this is the image that I just showed a few slides ago. So we have the woman, the incorrect caption, and the model is looking at the computer when it's making the prediction of the man in the image. I'm going to present a model which corrects this error. So here I mentioned the correct gender, a woman sitting in front of a laptop computer, and my model is also looking at the woman when it's describing the image. So I can say that my model is correct, but it's also correct for the right reasons. So I say this model is right for the right reasons. And I think it's important to think about the reasons why your models are making predictions, because sometimes you can be correct, but you can be correct for the wrong reasons. So here, the baseline model says a man holding a tennis racket on a tennis court, and it is a man, but the model's not looking at the man when it's making the prediction, it's looking at the tennis racket. So this model here is right for the wrong reasons. And you can imagine that this might be concerning because even though your sentence metrics might say that you're doing well, you might be a little bit worried about deploying a system that's looking at the wrong evidence into the real world. In contrast, our model is going to talk about the correct gender. So here, again, we say a man, but it's also looking at the person, so it's right for the right reasons. All right, so what is this model? Our model is called the Equalizer model. And we're going to start building our equalizer model by just taking a generic image captioning system. So we'll take our image I, feed it through a CNN, generate words with an LSTM, and then we'll train this with just a normal cross-entropy loss. All right, for understanding gender error, we particularly want to make sure that we're predicting the word man correctly. So we add a loss onto the model called a confident loss. And what the confident loss does is it encourages our model to be more confident about predicting the gender term. All right, so here we can see the person and we can see the gender evidence, and we want to be confident in predicting that gender term. But what if we have a scenario where we can't actually determine what the gender of the person is? And we create images that look like that by taking a segmentation mask and blocking out the person. And now we can't see the gender evidence, and so we shouldn't be able to accurately predict which term should be said in that orange box. So we'll take this blocked out image, which we call I.prime, feed it through a CNN, generate a sentence with an LSTM. We can use our softmax cross-entropy loss still, but for this word where we should be predicting a person word, we're going to tell our model to be confused a bit about which gender to predict. So hopefully by including this I' in this appearance confusion loss, we encourage our model to be unable to predict a gender given the context of an image. All right, so I'm going to formalize the confident loss and the appearance confusion loss a little bit more, so there will be a little bit of math. All right, so G sub m is the set of all male gendered words, and G sub w is the set of all female gendered words. I'm going to start building my confident loss with a batch size of size n, a sentence length of size t, and I'm going to use an indicator function to find all of the places in my ground true sentence where I should be talking about a woman word. And I'm going to multiply this by a loss f, which should be small when the model confidently predicts the gendered word woman correctly. And I'll have a symmetric loss for male gendered words. There's lots of different functions f which could measure this confidence. What we found to work was a quotient loss. So what this is, if we want to have a function f which is confident, or if we want to have an function f which is small when we're confident about predicting the female gendered words, we can have the numerator equal to the probability of predicting male gendered words and the denominator equal to the probability of predicting women gendered words. So this means our denominator gets big and we get more confident about predicting female gendered words, and our function f goes down. All right, so our appearance confusion loss has a similar form. So here, again, we have these images where we've blocked out the gender. We again have an indicator function to find all the places in our sentence where we should be talking about a gender term, and we multiply by this function c. And this function c should be small when our model is confused about which gender to discuss. And this is a pretty simple function. It's just the absolute difference between the probability of predicting a male gendered word and a female gendered word. So all in all, our equalizer model is really just this equalizer loss, where we're summing up these three different losses: cross-entropy loss, which is what you normally use to train your description model; a confident loss, which is going to encourage our model to be confident in making gender predictions; and an appearance confusion loss, which is going to make our model confused when making predictions when gender evidence isn't present. All right, and note that I didn't actually do anything with the structure of the description model. The entire model is basically just producing this new loss function. All right, so to train this model, I'm going to look at the MS-COCO dataset. In particular, I'm going to look at a subset of the MS-COCO dataset, which we call the biased dataset. We take this from prior work, men also like shopping, reducing gender bias amplification using corpus-level constraints. And basically, this biased dataset is the MS-COCO dataset where we only have images which contain either a man or a woman. All right. one thing that we want to be sure of when we're training our models and testing our models is we don't want to make the assumption that our training distribution is the same as our test distribution. So we also create what we call our balanced test set, where we artificially change the distribution of the number of men and women in the test set. So in the MS COCO data set, there's about 3 men for every 1 woman. In our balanced data set, we artificially make it such that there's 1 man for every 1 woman, so we're balanced. All right. Comparisons, I'm going to show a few different evaluations. I'll look at a baseline model, which is just a normal captioning model trained with a cross-entropy loss, a balanced model where at training time I sample the same number of men and women at train time, an upweight model. So in the upweight model, we note that we really care about getting the gender correct, so we'll multiply the cross-entropy loss by a scalar term for the gendered words, and finally the equalizer model, which is ours. All right. So the first metric that I want to look at is the distance to the ground truth ratio. And what this is measuring is if we're able to accurately predict a similar distribution of men and women words in our generated captions as our ground truth captions. So I look at the number of men and women captions in my ground truth descriptions, get that ratio, and then look at the ratio for my generated captions, and I want those to be the same. And we can see that the equalizer model is doing better on both the bias and the balance set. I can also look at error. So here I'm looking at gender error, and in particular, if I have an image of a man and I use a female gender term to describe the image, I'm going to count that as an error. But my captioning model can also output gender-neutral terms like person. I'm not going to count that as an error. And again, we see that the equalizer model is better. All right, so for these tests, I'm kind of clumping all of my examples of men and women images together, but I can also look at the breakdown across gender. So here I have 2 pie charts, so images of women and images of men, and in my baseline model, I can see when I'm correctly predicting the gender, incorrectly predicting the gender, and predicting a gender-neutral term. And what we see is that for images of men, our baseline model is actually doing pretty well. It's predicting the correct gender 75% of the time. But it's sort of doing this at the expense of our images of women. For images of women, we're predicting the correct gender less than 50% of the time. So this is a bit concerning. If we look at this breakdown for our equalizer model, though, we see that these 2 pie charts look much more similar. So here, for both the equalizer model, for both the images of men and images of women, we can see that about 60% of the time we're predicting the correct gender. So in some sense, you can say that the equalizer model is a little bit more fair in regards to predicting the correct gender. All right, so in this pie chart, I have 3 kinds of predictions we can make, correct gender, incorrect gender, or gender-neutral terms. And it's a little unclear what we should expect our prediction model or our captioning systems to predict. Should we expect them to predict the correct gender all the time, or is it okay for them to output gender-neutral terms? And one of the reasons why this is a bit unclear is that humans use different kinds of words when describing people. So here's an actual image from the MS COCO dataset, and you can see that 2 people have described the image using a male gendered term, so a man on a snowboard riding down a slope. 3 people, however, have decided to use a gender-neutral term, so something like person or snowboarder. So what do we want our model to do? And what we can do is we can define a threshold t and say that if at least t people use a gendered term when describing this image, we would also like our model to use a gendered term. And we can plot the accuracy of our model across different thresholds of t, and you see that for t equals 3, which corresponds to a max vote, our model is doing better. And in particular, you can see that as the threshold gets higher, our model continues to do better than the other models. And a big reason why that is that our model is a bit more cautious, and it will talk about people if it's unsure of the gender. And we'll see some qualitative examples in a bit. All right. We also want to know if our model is right for the right reasons. So the evaluation that we use to measure this is called the pointing game. And what we do is we look at those heat maps that show which part of the image is most important for making a prediction, and we see if the max activation of that heat map is within a person segmentation map. And if it is, we call it a hit, and we say that our model is right for the right reason. And again, you can see that our equalizer model is doing better than our baselines. All right. So for these evaluations that I've shown to sort of understand if we're mitigating gender bias in our descriptions, I've only been thinking about if we've predicted the correct word, the predict gendered word, male or female. However, one thing that we might think is that different objects in the image might influence our model to predict a gendered word. So next I'm going to be thinking about bias amplification, and specifically I'm going to be thinking about gendered words in the context of other objects in the image. So again, here are these nice pie charts that I showed at the beginning of the talk, and we can see that there's an amplified bias when looking at the male gender term. In the generated captions, we see man 50% of the time, and in the ground truth captions, we see man 50% of the time, and in the generated captions, we see man generated 57% of the time. And we can just formalize this and give a number for this bias by looking at the difference between these two values. And we can look at this bias amplification across all the different objects of MS COCO. And that's what I have plotted here. So on the x-axis, I have the different objects in MS COCO, and on the y-axis, I have an improvement in bias amplification between the baseline and the equalizer. And we can see that our equalizer model, on average, has a lower bias amplification, and if we look at the individual objects, we can see that our equalizer model has a better bias amplification across more objects than our baseline. All right, so some qualitative results. Here we have the baseline model predicting the incorrect gender again, and it's looking at the cat while mentioning the word woman. So there's a weird bias in MS COCO that I guess women like cats better, and there's more images of women and cats. The equalizer model, on the other hand, predicts the correct gender and also looks at the person's face. This is a harder example. So again, we have a person with a computer. The model sees the computer and thinks that there must be a man in the image. In contrast, the equalizer model is a little bit more cautious, and it says a person is with the computer. And this image is really hard. It's kind of hard to tell with the heat maps, but you can only see the person's hands, and so it's kind of hard to decide how to describe this image. All right, finally, our model isn't perfect. So here we're predicting the incorrect gender. We are looking at the right location in the image, though. All right. So thus far, I've just been talking about gender bias, but there's lots of other kinds of biases that our model can pick up on. So next, I'm going to be talking about a particular kind of error that can arise from bias in training sets called hallucination, and this was work that was presented at EMNLP 2018. All right, so here we have an image of some women holding cell phones, and we have two sort of top models in the visual description world, NBT, which is the neural baby talk model, and top-down, the top-down model. And we can see that both of these descriptions are capturing women. They're capturing the fact that they're talking on cell phones, but the neural baby talk model is making one key error. It's talking about a bench, and there's no bench in the image. Well, hopefully, our standard image captioning metrics will capture this, and we'll see that our NBT model has a worse score than our top-down model. And this isn't quite the case. Our MBT model actually scores higher on cider and spice than the top-down model, even though it's hallucinating this object bench. So if we really want to understand this hallucination error by looking at metrics, it seems like we can't always rely on these standard metrics. So the first thing we did is we proposed a metric called chair, which explicitly measures whether or not objects are being hallucinated in image captions. And for chair, lower is better. Usually higher is better, but for chair, lower is better. And we can see that chair shows us that the top-down model is not hallucinating an object. All right, we have two forms of our chair metric, a sentence level and an instance level. And it's pretty simple. So for the sentence level, we're just looking at the number of sentences which include a hallucinated object over all sentences, whereas for the instance level, we're looking at the number of hallucinated objects in total over our test set over all objects that are mentioned in our test set. And one thing that we found was really important is that when determining hallucinated objects, it's important to use ground truth segmentations as well as ground truth captions. So one thing that will happen is that people, when they're describing an image, they might not mention an object, but in the generated caption, that object will be there. So we don't, or in the generated caption, that object will be there. And we don't want to penalize our generated caption for mentioning an object just because the human annotators didn't mention it. All right, so the first question I want to ask is which models are prone to hallucination. And here I'm going to be showing spice cider scores where higher is better and chair where lower is better. And I'm first going to look at two models, the LRCN model and the fully connected model, which were state-of-the-art circa 2015, 2016. These are non-attention-based models. The important difference is that in the LRCN model, we're inputting our image feature at every single time step, whereas in the fully connected model, we just input our image at the start and then generate our sentence. And somewhat surprisingly, we find that inputting the image at every single time step increases hallucination. All right, so most people don't use these models. Most people are going to use an attention-based model. So here I have the FC model compared to a variety of different attention-based models that have been proposed over the last few years. And we see that in general, overall, the attention decreases hallucination. All right, there's a lot of differences, though, between our fully connected model, which is our non-attention-based model, and our attention-based model. So to do a slightly cleaner ablation and understand how attention is decreasing hallucination, we do a test where we take one of our attention-based models and take out one component one at a time. So the top-down model is the model we choose, and it's just a pretty common attention-based model. And the first thing we try and do is that we take out the attention by mean pooling over spatial con features, as opposed to using an attention mechanism to decide which spatial features to look at. And we see that this does increase the hallucination a little bit. But what really increases the hallucination if we take away this con features completely. So attention does decrease our hallucination, but somewhat surprisingly, it seems to be that this is mainly due to the fact that the models have access to these spatial convolutional features. All right. One thing that's become really popular in training description models is to use a self-critical loss. And the self-critical loss is a loss that basically directly optimizes for sentence metrics, in particular CIDR. And what we see is that if we use a self-critical loss, our hallucination increases. And there's been a few other papers that have talked about issues with the self-critical loss. This is another issue. It seems to be increasing hallucination. And finally, something that was somewhat surprising to us is we also looked at training a model with an adversarial loss. And even though the adversarial loss decreases scores like SPICE and CIDR, it decreases hallucination as well. All right. So in total, which models are prone to hallucination? We find that for models without attention, inputting the image at every single time step increases hallucination. Attention decreases hallucination, but mainly because of access to convolutional feature maps, and the self-critical training also tends to increase hallucination. All right, what are the likely causes of hallucination? So this is a really interesting question, I think. So below I have a generated caption, a plate of food with broccoli and a fork. There's no fork in the image, and we might want to ask, are we making this error because our image model thinks there's a fork, or are we making this error because there's some learned bias? And so what we do is we train an image model which shares the weights with our image captioning model to predict which kinds of objects should be in the image. And we see that our image model is predicting bowl, broccoli, carrot, dining table, but not fork. However, if we look at our language model, which is trained to predict a word given all the other words in a sentence, we see that our language model predicts the word fork, spoon, and bowl. So we might want to think that this particular error is more consistent with an error from the language model as opposed to an image model. And we can measure this holistically across different models, across our entire test set. And the trend that we see is that when models hallucinate less, they tend to be making errors that are more consistent with their image model. Whereas when models hallucinate more, they tend to make errors that are consistent with the language model. So basically what this is saying is that over-relying on the language model is going to perhaps cause you to hallucinate more. Finally, do standard metrics capture hallucination? So we already saw in an example that that's not always the case. Here we quantify this, so we're looking at the correlation between different metrics and the chair metric. And we see that though SPICE correlates the best, none of them correlate particularly well. Another thing that we might want to think about is if we can use our chair metric to we want to see if our chair metric can help us understand if our captions correlate better with human preference. So here we have a correlation between different metrics and human preference. And we can see that if we take our metric and then just add our chair score on top of it, we see a higher agreement with human preference. So chair is complementary to our standard image captioning metrics. All right, so to answer the question, do standard metrics capture hallucination? Not all the time, and in addition, our chair metric is complementary and can allow us to get a better understanding on whether or not our sentences are more preferable to humans. Okay, so in conclusion, in this talk, I've discussed bias and the kinds of errors that bias can cause in image captioning. For gender bias, I've presented the equalizer model, which can correct bias to some degree. And I've also talked about this error of hallucination. And we've presented a metric, the chair metric, to explicitly measure hallucination. And we've talked about how this can allow us to analyze sources and causes of hallucination. I think there's a lot of interesting directions moving forward. So in particular, I think one thing that's important to think about is how do we know when context will help us make the correct decisions, and how do we know when it's going to lead us to bias? So in the gender prediction, I made this really, pretty hard constraint that I never wanted to consider bias when predicting somebody's gender. But I think for a lot of different kinds of predictions, we might want to be considering, the context of an image. So for example, though it might not be okay to say a woman is in the image because though it's not okay to say there's a man in the image because you see a computer, it might be okay to assume that maybe there's a keyboard or a mouse in the image because you see a computer. I also want to think about how we can correct bias with less supervision. For our equalizer model, we actually required quite a bit of supervision. We needed person segmentation masks for every single image. And finally, here I've talked about bias for image captioning, but thinking about bias in more complex tasks I think is really important. So for example, dialogue. All right, so that's all I have, so thank you.
Maybe 2 quick questions, and if there are more questions, feel free to come to the panel discussion at the end of the session. So, questions?
Yep.
I have just a question regarding centric strain.
Uh-huh.
What was the context? Was it trained with fully connected, or was it trained with attention?
We trained with lots of different models. So, and I guess one thing that I didn't mention here is that for the fully connected and for the models that don't have attention, the self-critical loss didn't decrease hallucination. It just uniformly made the outputs better. But for the models with attention, we tried 4 different models. It always. No, it wasn't ensembled.
So yeah, I think this the thing is that it needs to be trained. The best model needs to be trained with spice and cider. The spice will reduce a lot the hallucination. This is
Okay, yeah, that's an interesting point. Yeah.
Any more questions? All right. Is there a question?
Yeah. I'm wondering, is hallucinations always bad? Because in the data example, even though there's no flow in the picture, but the captioning model gives there is a flow. So, but it can also recognize yeah, there's this is a plate with a flow. So OAET flow we should use so basically I think it's probably an extension.
Yeah, I mean, I guess it's kind of questionable. I mean, you don't see the fork, so if you're defining your image caption model as being something that can describe what is in the image, then it's a clear failure mode. But perhaps if you want your image captioning model to be sort of understand the kinds of things that make sense in the world, then maybe it's not as big of a concern. But if you're operating with the assumption that you want your image captioning model to be saying exactly what's in the image, then I think it's a pretty clear failure mode. And also another thing I didn't mention, but my co-author Anya has run the movie description challenge for quite a few years, and that's one thing that people mention as being a really bad error is when the model hallucinates an object that's not in the video.